Hey Phys2 kids, Campbell here. In this video, we're going to talk about what is probably not maybe the most important law of thermodynamics, but for you in Phys2, it is the first law of thermodynamics. Now, in order to talk about it, we got to flash back to the past. In AP Physics 1, you learned all about the law of conservation of energy, that the total energy of an isolated system stays constant, just gets transformed into, different types of energy like kinetic and potential and thermal and chemical and whatever. Now, in thermodynamics, we can consider this isolated system to be the internal energy of our sample. So our gas molecules or our solid or a liquid, those energies, right? And for ideal gases, remember, there's no potential energy, no bonds or associations forming. So it's just the kinetic energy. Now, you also learned back in Phys 1 that you can transfer energy into or out of a system via work, which you talked about in AP Physics 1, but heat is a new one you didn't talk about then. We're going to talk about it now because it's thermodynamics. Now, the most misused word in our vocabulary is heat. When you think of heat, you think, oh, it's so hot. Because, H and T starts with H, ends with T. But heat and hot are totally different things. Heat, symbolized by a Q, is a transfer of thermal energy. It's a process. It is not a temperature. But your brain associates heat flow with temperature changes. Remember, temperature is a measure of the energy of the molecules, that internal energy, that kinetic energy. Remember that internal energy is N3/2 kBT. Q, not Q. Not Q. Temperature is a measure of the internal energy of the system. And yes, sometimes when heat flows, temperature goes up. But if heat is flowing in and work is coming out, well, temperature might not change at all. So, changing the internal energy of our system can happen through heat. When a system is gaining thermal energy, when heat is flowing into a system, that we term that a positive Q. When a system loses thermal energy, when heat is flowing out of the system, that's a negative Q. Now, that doesn't mean the temperature is going up or down. It just means that it's coming in or going out. Work can be done by the system or on the system, but only if the volume changes. Remember that work, defined in AP Physics 1, work is a force times a distance. And so there has to be a distance, a motion, in order for work to be done. If the force is in the direction of motion, that's a positive work. If the force is in the opposite direction of motion, that's a negative work. So in Physics 1, you learned a lot about how friction does negative work and it takes energy out of the system. Well, we won't be talking about friction now, but just a little reminder how that works. So work and heat are processes, not states. Now, work we can actually calculate directly. So if we go back to our work equation, work is force times distance. And we know that pressure is force over area. We learned that at the second video from our summer assignment. If we put these together, we get work is equal to pressure times area times delta x, area being like the surface area, x being the distance something moves. And of course, from a Puvnert standpoint, we want to think of that area times distance as a change in volume. Now, you're probably like, wait, where did the negative come from? Well, this is the equation that is on your equation sheet. It looks just like this, but this is actually work on the gas. And it's important to know that that is work on the gas. And work on the gas is equal to but opposite by Newton's third law, the work done by the gas. So what the heck? What do you mean work on, work by? Okay, so here is a gas in a chamber with a movable piston. So this little thing right here can move back and forth. If we drew a free body diagram, which it wouldn't look like that because you don't draw arrows pointing at stuff, but we would have, there's the force that the gas exerts, and there is the force, maybe that I'm going to call it, it's external, but it's the work on, that's what we're doing. We're pushing, man. So if we push on the gas, right, and we compress the gas, then the work done by us is positive. So in a compression, we are doing work, and so the work done on the gas by us is positive, but the force of the gas, right, is to the right. It's like trying to push it out. Get this thing away from me. I want to go down to lower pressure. It is opposite of the displacement. So in a compression, the work by the gas by the gas's force is negative. And that's the point of this little negative sign here, right? Because we always do final volume minus initial volume. It's always final minus initial, no matter what we're calculating a delta of. And so if our final volume is less, this is going to give us a negative change in volume times a negative, which is going to give us a positive work on the gas. Now, if we talk about an expansion, so if volume is increasing, right, that's what it means by an expansion, volume is increasing, that means that it's pushing against us. So the work by the gas, the work is being done by the gas, right? The gas is pushing out that piston. So the work done by the gas is positive, but the work done on the gas is negative, and so we would come out with a bigger final volume, right? So then we would get a negative for work. So, but it's important to be able to visualize what is happening in the signs for work, because another way you can get work is by the area under a PV graph. And anytime you have an equation that's something times something, the area under those somethings on a graph are going to give you that quantity. So the area, and it's the whole area. So like this would be a isobaric process, right? And so we would take this whole area here and calculate it. And of course, we're going to get P delta V. And that's when you have to remember a compression is positive work. An expansion like this, if this is an expansion, this is negative work on, because it's expanding as it goes from the initial to final volume. So in order for a gas to do work, that means its volume has to change. It doesn't matter if the pressure changes, the volume has to change. Now, we can only use the equation, work is equal to negative P delta V, if the pressure is constant. So if, that wasn't supposed to build with that, but if I have a non-constant pressure, I'm going to have to do area. Now, this is Phys 2. We don't do calculus. There's no integrals here. So if we had a process that looked like that, they'd actually draw it like this, because we can calculate the area under a triangle and a rectangle. So no calculus, no integrals, don't worry about that. But we can use the area if pressure is not constant to get the work done in that process. Now, what type of process always has zero work done on or by the gas? Well, that would be something where the volume doesn't change, right? So isovolumetric has zero work done, which means that the flow of heat and the change in temperature works with your brain. Doesn't always do that. Does for isovolumetric processes, because there's no work. So heat flows in, temperature goes up, because the internal energy is going up. That's why. So here is the first law of thermodynamics. Delta U, our change in internal energy, which is a state function, by the way, it is measurable, because you can measure temperature, is equal to heat plus work, and this is work on again. So again, they don't write on your equation sheet, but all the work equations in thermodynamics are work on the gas, the work that we are doing, the external force is doing, not work by. But those are processes. They're things that are changing the amount of energy. Now, remember that delta U is also N 3/2 kb delta T. So if you're ever asked to calculate heat, you calculate delta U, you calculate work, and use those to find Q. So as a general rule, though, the internal energy, which means the temperature, of a system increases if energy is added via heat or work done on the system, not by the system, and decreases via work done by the system. The system itself is doing the work. It's getting tired. It's pushing that piston out, and heat being removed from the system. So you saw this in our PV diagram video, same exact thing. But this time, let's find the work done in each process and then the net work. So if we look at process 1 here, process 1 is an isovolumetric process. Well, that's easy. That's 0, right? If work is negative P delta V, if there's no delta V, there's no work. So that means that work in number 3, let's get the easy ones out of the way, that's also 0. Now, what about process 2? Well, work done in process 2 is this entire area here. It's not just the area underneath to that line, it's the entire area. And so our delta V is 2, right? 3 minus 1 is 2, and our P is 1. So we have a change our P is 1. Our P is 2. This whole axis here, we're going to do math. So it's 2PO times 2VO, which gives us 4, right? 2 times 2 is 4, 4 POVO. Now, let's look at the sign. This is an expansion, which means volume's getting bigger. So if we're talking about work on, this is a negative amount of work because the gas is the one doing the work. We are not. Now, if we look at, again, this was for process 2. I meant to write that down. So work for process 4, again, we're talking about work on. We have that same change in volume, but here, so process 4 is this amount right there. So that's only 1 PO times the 2 VO, so same volume change. And so that gives us 2 POVO. Now notice this is a compression, so we are physically doing the work. We are pushing in. And so our net work is the sum of the works. So work net, that's supposed to be a W, is equal to the sum of the works. And so if I add these two together, right, we're going to get a negative 2 POVO for our work. Now, in a cyclic process like this, you can also get the net work by the area enclosed. So if we take a look at this and we calculate the area enclosed, so I'll kind of shade it diagonal here. This is the area enclosed, which is a 2 PO minus 1 PO, so that's 1 PO, and that's our 3 minus 1, which is 2. And so the area enclosed, again, 2 PO VO, and remember that this, the bigger part, the top line, defines whether or not we are positive or negative for our work, and because it's an expansion, that's negative work on. So we still get the same answer. So you can do more math or less math if we're asked for net work. You choose. What about, spoiler alert, the net change in internal energy. Oops, slow build there. The net change in internal energy, remember that internal energy is not heat. It is N times KB times, I forgot the 3 halves, times delta T. Now, in my total process, right, I start here, I go here, I go here, I go here. I'm back to where I started, which means I'm back to my original temperature, which means there is no change in internal energy. Huh, pretty cool. All right, let's take a look at a bigger one. I want you to pause the video, and then I want to see if you can calculate these things, and then check. So pause the video, see if you can do these in your packet, and then put me back on. All right, let's check how you did. First, work from A to B. Well, that's pretty easy, right? Work A to B is just equal to 0. No biggie. Isovolumetric, no delta V, no work. All right, work from B to C. Now, this is the work under the process, B to C, which is an isobaric process. And so it's the area under the curve, and I threw a little curveball at you because notice your units. atmospheres cannot be used with meters cubed to get joules, right? The unit for energy is joules, so work is joules. So when we do our area here, we're going to have to convert atmospheres to pascals. So if you go to your equation sheet, you'll see that the unit, well, actually they list it as 100,000, but 101,300 is what I use because that's, that's how many pascals there are in atmospheres. So we're just going to take that 1.4 atmospheres and we're going to multiply it by 101,300. So there is the height of this process. Now we're going to multiply by the change in volume, but notice that the biggest mistake students make is they forget that there is something on the scale. So it's not just 10.7 minus 6.8, it's 10.7, our final volume, times 10 to the negative third, minus 6.8 times 10 to the negative third. Did you miss that? It's easy to miss. If you do that, the quantity you're going to get is 533 joules. But this is work on the gas, the work that we're doing, and our force is in, and the piston is moving out. It is an expansion, so that's negative work on. All right, now the gas is then taken from C to A. So we're going to go from A to B to C to A. Notice that this is an isotherm. How do you know it's an isotherm? It's an isotherm because the ratio of 2.2 to 6.8 is the same as 1.4 to 10.7. So that means that TA must equal TC by the ideal gas law. Now, the network, remember I said in the last problem we did, is this area that's enclosed. And since this is a compression where we're physically squeezing the gas, that means that the network is positive. Now, the total change in internal energy, it just says A to C, but it doesn't matter if we're talking A to C or A to C to A, because this is an isotherm, there's no change in temperature, and therefore there is zero change in internal energy, because remember, internal energy is not heat. It's 3/2 kB delta T. If there's no change in temperature, there's no change in internal energy. All right, well, that brings us to how we figure out if heat is flowing into, out, or not flowing to the gas. Now, your brain wants to say, oh, there's no change in temperature, so there's no heat flow. But there has to be, right? Because the first law of thermodynamics says delta U is Q plus W. And we just said that this is positive and this is 0. So that means heat actually has to flow out of the gas. So that means that Q is negative, right? That's got to be negative if our network is positive and there's no change in temperature. Well, how did you do? All right, this is your Google form question. It's also in your notes packet. So answer that. Give me any questions you have about this video in your Google form, and I'll see you in class.